Hi class, today we're going to be talking about molecular polarity. So the underlying goal of today's class is to be able to work from a molecular formula to a Lewis structure to determining the valence, the VSEPR theory geometry, to determining whether or not it's polar or nonpolar. So our goal is to determine if a molecule is polar or nonpolar. A polar molecule is one that has an uneven electron distribution around the whole molecule. So this is an expansion to whether or not a bond is polar. If you have not yet watched the video on bond polarity and done the quiz on bond polarity, stop now. Go back and watch that first and then come back to this video, because if you don't understand what determines if a bond is polar or nonpolar, then you're not going to be able to determine whether a molecule is polar or nonpolar. So in bond polarity, we looked at whether or not electrons were shared unevenly across a bond between those two atoms. Now what we're doing is taking that a step further and thinking about whether or not the electrons are shared evenly or unevenly around the whole three-dimensional shape of the molecule. If a molecule has uneven electron sharing, then it has a negative pole and a positive pole, or a negative side and a positive side, and it's considered polar. If the electron distribution is even, then it's considered nonpolar. It doesn't have positive and negative ends. Polarity, Okay, so let's just take a few notes over the information I just covered. We are studying molecular polarity. What we want to do is know whether or not a molecule is polar or nonpolar. So a polar molecule has positive and negative sides. It's not charged, it's neutral, but the electron distribution is uneven. A nonpolar molecule has even electron distribution, and so it doesn't have positive or negative ends. So I'm going to be honest with you. Determining whether or not a molecule is polar or nonpolar is, it's sort of a tricky skill. You have to be really, really good at three-dimensional visualization. If you aren't, then determining whether or not a molecule is polar or nonpolar is going to be really hard. So on the next page, I'm going to go over a flow chart that I created to help you figure out whether or not a molecule is polar or nonpolar based on some of the sort of features we need to look for. So I like to think of polarity as a tug-of-war game, where you have your central atom and your outer atoms are playing tug-of-war on that central atom. So every outer atom has a rope to that central atom, and those outer atoms are pulling on that central atom. And you can think of the outer atom's electronegativity as sort of a measure of how strong it can pull on that rope. Okay, so if all the outer atoms are equally strong and they're pulling in ropes in equal but opposite directions, that center atom isn't going to move. And if that center atom isn't moving, then you should have a nonpolar molecule. That means that everything is distributed evenly around it. If that center atom ends up moving, then you have a polar molecule. Some area is able to pull electrons towards it more than other areas of the molecule. So an example of two sort of simple molecules that we can think of are carbon dioxide and water. Carbon dioxide is a carbon, and it's double bound to an oxygen, double bound to an oxygen. So carbon in the center, 2 oxygens on the outside. The oxygens both have the same electronegativity, and they are pulling opposite of each other on that center carbon atom. CO2 is a linear molecule, so it's carbon in the center, oxygen, oxygen. They're pulling equally. Carbon's not going to move. Nonpolar. That's despite the fact that the CO bond is a polar bond. So just because you have a polar bond doesn't mean you have a polar molecule. Now water, H2O, is oxygen in the center, 2 hydrogens, and 2 lone pairs of electrons on that oxygen. So it's an AX4 tetrahedral parent geometry, but because of the 2 lone pairs, it's a bent molecular geometry. So you have oxygen in the center, hydrogen, hydrogen. And those 2 hydrogens have the same electronegativity, and they're going to be pulling on that oxygen atom. And yes, they are pulling with the same force, but there's nothing up here pulling this way. And so that oxygen atom would get moved down, that center atom would get pulled down by those 2 hydrogens pulling on it. Water is a polar molecule. The oxygen side is negative and the hydrogen side is positive. So let's take a look at the flow chart and go over some of the properties that we're going to be looking for when we try to figure out whether or not a molecule is polar or nonpolar. And then we'll go through some examples of this whole process. Okay, so when you first look at this flow chart, it might seem a little bit overwhelming. This is posted on Canvas and available for you to use. Normally, I would tell you need to learn this, but given the sort of condensed time frame that we are covering this material in, and the class is missed because of switching to online, I'm going to let you use this flow chart for the exam. So you don't need to memorize it, but you do need to learn how to use it. So we start up here at the start spot, and the very first question we have to ask is, are we looking at something that is ionic? So what we're thinking here is this a polyatomic ion or is it a neutral molecule? If it's a polyatomic ion, if your answer is yes to that question, then it's polar. All ions are polar because the whole thing is charged. So you don't have to go any further with it than that. If your answer is no, it's a neutral molecule, then you're going to move here to the next question. Are there lone pairs on the central atom? If your answer is no, then we're going to think about, are all the outer atoms the same type? If the answer is yes, then it's nonpolar. This particular pathway here, no lone pairs on the center atom and all outer atoms the same type, is a really, really common one. And anytime you can answer no, yes to those 2 questions, you have a nonpolar molecule, something with even electron distribution. Okay, if all the outer atoms were not the same type, if you answered no, then you're going to look, are any of the bonds polar? If the bonds are not polar, then we're back to nonpolar. If the bonds are polar, then we want to think, are they symmetrical or not? And again, this is where it starts to get tricky. Are they symmetrical or not? Because we have to have that 3D sort of sense of symmetry. Generally speaking, you want to say, is there something equal and opposite of it? So if it's symmetrical, then it should be nonpolar. If it's not symmetrical, it should be polar. All right. Let's go back up to lone pairs on the center atom. If we answered yes to the question, there are lone pairs on the center atom, then the next question we want to ask is, are all the outer atoms the same type? If the answer is yes, then we're going to say, okay, was it symmetrical? Yes, then it's nonpolar. All the outer atoms the same, all the outer atoms the same type? Yes. Symmetrical? No. So now we're down here in this path. Polar. Back up here to all outer atoms the same type. If we answered no to that question, we're at polar. So this is also sort of one of those quick questions. Lone pairs on the central atom, yes. All outer atoms the same type, no. It's going to be polar every single time. So we sort of have these two pathways that we're going to see a lot. And I'm going to point those out in sort of a different color here. So all outer atoms the same type and no lone pairs. This first pathway is a common one to getting a nonpolar molecule. The second pathway here, which looks a little bit longer, but it's not. It's still just two questions. Lone pairs on the outer atom and not the same outer atoms gives us a polar molecule. Generally speaking, most of the time when you have lone pairs on the central atom, you end up with a polar molecule. There are a few exceptions though, particularly in high electron domains like AX5 and AX6. If you have enough lone pairs on one of those, you can end up with a linear molecule. So there are lone pairs on the center atom, but it's still linear, and so it ends up being nonpolar. But most of the time when we have lone pairs on the central atom, we end up with an unsymmetrical structure and it ends up being polar. Okay, we're going to start putting this whole thing together like I discussed. We're going to start with the formula, Lewis structure and geometry, and then determine whether or not something is polar. The hybrid orbitals, sigma and pi bonds, not that one. Let me erase that. We're going to look at that one. The hybrid orbitals and sigma and pi orbitals, just ignore for now. We're coming back to that topic tomorrow. So for now, what we're going to focus on are this column, this column, this column, and this column. Ultimately, what we're really after here is polarity and Lewis structure and geometry. We already know how to do Lewis structure. We've reviewed the different geometry types, but we're going to see how that comes together now and go through a few examples here. So some of these compounds that are listed here are ones that were on the worksheet, the Lewis structure worksheet. Some of them are new. You can find this valence bond theory, VBT, and polarity worksheet on Canvas to download. Again, if you're able to, I'd really recommend printing it out to work inside of it. Otherwise, just duplicate this on scrap paper or something. Okay, so we've made the Lewis structure for CO2. We did that on the Lewis structure worksheet. And we found that its Lewis structure looks like this. It does have some possible resonances with a triple bond and a single bond, but those structures aren't as stable as this one, so we're going to just base it on this one. Okay, so when we want to determine whether or not a molecule is polar or nonpolar, one of the things we have to look at is the difference in electronegativity of the bonds. That's what this stands for. That it should be a chi. It's that electronegativity from your periodic table. So for carbon dioxide, we only have one bond type, a CO bond type, and it doesn't matter if it's a single, double, or triple. We're just looking at the difference in electronegativity. Oxygen is 3.5, carbon is 2.5, and so that gives us a delta chi of 1. That means that this molecule does have polar bonds. Are there any lone pairs on the central atom? No. Are all outer atoms the same type? Yes. So there's multiple ways to get to the answer of whether or not this molecule is polar or nonpolar. And we already know it's nonpolar because I discussed it a couple minutes ago. But there's two ways we could have answered that. We could have said there were polar bonds, but they're balanced. How do I know they're balanced? So what I would say is, if I go back to the Lewis structure, if I cut it in half this way, is it the same on both sides? Yes. If I cut it in half this way, is it the same on both sides? Yes. If you can answer yes to both of those questions, it's balanced. So a molecule that's balanced, even though it has polar bonds, would be nonpolar. The other way we can do it is using the flow chart. This is not an ion. There are no lone pairs on the center atom. All outer atoms are the same type. That's one of our we should know lines because it happens so often. So when those things are true, it's nonpolar. Okay, let's try another one. Methane, CH4. So we made the Lewis structure. It looks like this. Oh, I forgot to put geometry up here. So CO2 was linear. This one ended up being tetrahedral. It is an AX4, and there's no lone pairs on the central atom. So it is tetrahedral molecular geometry. If we were really drawing this Lewis structure to show that, we would kind of have to show those two V's in that structure, but we don't have to do that for here. Okay, delta chi between carbon and hydrogen. Carbon is 2.5, hydrogen's 2.1. So that means there are not polar bonds. We only have non-polar bonds. There's no lone pairs on the central atom, and all outer atoms are the same type. So there's a few reasons here why this molecule is going to be non-polar. Back to that same line of thought, no lone pairs on the central atom, all outer atoms the same type. That's going to tell us it's polar. Another thing that's going to tell us it's polar is that we have all non-polar bonds. We don't even have any polar bonds. So often when you have something that has all non-polar bonds, you have a non-polar molecule. Okay, let's skip ahead a little bit here to one that's kind of interesting. We've already discussed water. We know it's polar. PF5, I'll let you try that one. CHCl3. This is a molecule known as chloroform. Its Lewis structure, when you do the Lewis structure, you end up with something that is tetrahedral. So it's sort of like CH4, which we just did above, except that 3 of the hydrogens have been replaced by chlorines. There's still no lone pairs on the carbon. So we know that the delta chi of the CH bond is 0.4 because we just found that above. The Cl carbon bond is 3.0 minus 2.5, so 0.5. So this would fall into the polar range. So what would we kind of do here with our feature check? So our feature check isn't an answer, it's just a way of keeping track of what we have. So we have polar bonds, we have non-polar bonds, we have a mix of both. Are our polar bonds balanced? No. How would we know that? Okay, so again, if I cut the molecule in half this way, is it the same on both sides? Yes. If I cut the molecule in half this way, is it the same on both sides? No. Why not? This is a hydrogen and this is a chlorine. They are not equally strong, right? Remember I said think of electronegativity as how strongly something is pulling on this rope. So we have hydrogen pulling on the rope and chlorine pulling on the rope. Chlorine is stronger. That means that we're we're going to end up with sort of a partial negative charge down here by the chlorines and a partial positive charge up here by the hydrogens. So this molecule is polar. Okay, let's move on to the second page and do a few examples off of here. I'm actually going to jump all the way down here to SOCl2. This was one of the molecules that I think we had on our other worksheet. The Lewis structure, sulfur is in the middle, and we have 2 chlorines. And the oxygen up here. The molecular geometry here is trigonal pyramidal. Okay, so this it is in AB3E. It has 3 bonds to outer atoms and E, 1 electron pair. If we sort of think about our delta chi values here, we have 1 for sulfur and chlorine and 1 for sulfur and oxygen. So sulfur and oxygen end up being 1 apart, and sulfur and chlorine end up being 0.5 apart. Sulfur is 2.5, oxygen is 3.5, and chlorine is 3. Remember, those values are just on your periodic table. So we have polar bonds. We have lone pairs on the central atom. All the outer atoms are not the same type. And so can we say, are our polar bonds balanced? Well, there's a chlorine on both sides, so they kind of balance out, but there's nothing on the opposite side of the oxygen, so those are not balanced. So no. What do you think? Do you think this one is going to be polar or non-polar? It is polar. I hope you figured that out. I'm not going to say guessed. I hope you didn't have to guess. I hope you knew. It's not balanced, right? So if I cut the molecule in half this way, it is the same on both sides, but when I cut it in half this way, it's clearly not the same on both sides. Another way we could have known that is that there are lone pairs on the central atom and all the outer atoms are not the same type. And that tells us right away that it's polar. Okay, so when we're talking about molecular polarity, we could start to expand this to some organic molecules like I have on this sheet. I do not expect you to be able to do Lewis structures for organic molecules. It's beyond the scope of this course. So this one, and this one. You don't have to be able to draw the structures. But if I give you the structures, you should be able to determine if it's polar or non-polar. So I'm going to give you the structure here. This molecule consists of 3 carbons bound to each other, then to an oxygen and a hydrogen. And then there are hydrogens off of all the carbons to make its octet complete. Okay, acetone, it looks like this. It's a carbon double bound to an oxygen, and then it has another bond to a CH3 group, which looks like this. And ethene is 2 carbons double bound to each other, and then each carbon has hydrogens off of it. So that's what these structures look like. You can determine whether or not it's polar or non-polar. Again, we're looking for uneven electron distribution across the whole molecule. If we come up here to the one at the top of the page, we are going to think about a couple things. First of all, we have this whole grouping of C and H. And we've seen on the previous page that the CH bond is 0.4 or nonpolar. But then we have this oxygen thrown in there, and the oxygen creates a sort of polar spot. I forgot my lone pairs on that oxygen. That oxygen has 2 lone pairs. Okay. So that oxygen induces a polar spot. And so even though there's only one of them, the whole molecule would be considered polar. The whole molecule is not symmetrical, right? If I cut it in half this way, it would be, but if I cut it in half this way, it's not, right? There's no counterpart to this oxygen to balance it. So it's a polar molecule. Acetone, again, we have this mixture of polar and nonpolar bonds. There are no lone pairs on the central atom, which would be this carbon is sort of thought of as the central atom. So would this be polar or nonpolar? There should be 2 lone pairs on that oxygen too, sorry. Polar or nonpolar, what are you thinking? All right, so if I cut it in half this way, it's the same on both sides. But if I cut it in half this way, it's definitely not. I don't have anything to balance that oxygen. So acetone is polar. Ethene, this is going to be a lot like methane or CH4 was on the other page. It's all nonpolar bonds. And that's it. It's all nonpolar bonds. There's no lone pairs anywhere, anything. So this ends up being a nonpolar molecule. So you should finish filling out this worksheet, and then you can look at the answer key that's posted on Canvas to check and see how you did. I'm going to post a follow-up participation quiz on this subject matter, so you can check it. Again, your goal here is to be able to work from, so let's say, for example, to work from something like a structure, determine the Lewis structure, identify the geometry, and then determine whether or not it's polar or non-polar. We should be able to string all of that together at this point in time. On Friday, we're going to talk about the last subject material in Chapter 9, which is valence bond theory. In that, we're going to learn about orbital hybridization and be able to fill in the last 2 columns of this, as well as be able to finish filling in that geometry chart.